Did you know that lots of animation and VFX studios don't want to use the render engines we use as 3D artists, like Redshift, V-Ray, Cycles, Octane, and others, because they want more than that? So in today's video, we're gonna take a look at the secret render engines used by big VFX studios like Wētā FX, Framestore, and Animal Logic, which you cannot even dream of touching. But on the other hand, animation render engines like Pixar's RenderMan and DreamWorks' MoonRay are available to use right now. On the other hand, Disney's Hyperion is totally proprietary, so it is actually a secret tech. I want you to stay till the end because this video has lots of interesting information, but most importantly, I want to tell you at the end about the studio that built a whole render engine in more than a year of hard work to solve one of the biggest rendering problems ever for one single project, and they never used it again. One of the most fascinating engines is Manuka from Wētā FX, which started, I would say, almost like an internal experiment, rather than a project to replace the studio's render engine, because obviously they had to use commercial render engines at first. You see, around the 2010s, Wētā Digital had a very mature pipeline, built mostly around Pixar's RenderMan, in addition to its own tools such as PentaRay for dealing with enormous scenes. But Wētā's movies were becoming increasingly brutal for any render engine. I mean thousands of objects, enormous environments, extremely detailed creatures, dense fur, complex materials, a lighting that artists wanted to treat more physically rather than constantly cheating, if you know what I mean. So the solution was their engine called Manuka, which started as a small R&D path tracing platform, but the results were promising enough that Wētā gradually turned it into a production render engine. And here's the thing, RenderMan has served the studio extremely well, but the problem was that Wētā wanted a render engine designed around its pipeline, because as you know, they always deal with extreme scene complexity, so they wanted something that allows them to control everything, from shading, lighting transport, to memory management, and especially integration with its other proprietary tools. The payoff was that Manuka's physically based approach also reduced the amount of special case lighting tricks which artists needed, because it gave them the ability to build physically plausible materials and lights and let the render engine simulate how light actually travels throughout the scene. But the transition between RenderMan and Manuka happened gradually through actual movies. Dawn of the Planet of the Apes, back in 2014, was essentially Manuka's big production test, because most of their movies still used RenderMan, but Wētā tried Manuka on particularly nasty shots, such as the ape confrontation, where huge numbers of high-detail furry characters could otherwise create serious memory problems. And it worked so well that Manuka became the primary render engine on The Hobbit, the Battle of the Five Armies, helping Wētā tackle Lake Down's destruction and the enormous final battle. And by the War for the Planet of the Apes back in 2017, Wētā had moved the entire film to Manuka because the studio could render dozens or even hundreds of high-resolution furry apes, and they did this together, instead of relying heavily on simplified assets and fake fur. So Manuka since then became the most important part of their lighting and rendering system, and it was even pushed much further for projects such as Avatar, The Way of the Water, working alongside Wētā's interactive gazebo render engine, so Wētā artists could preview lighting that translated closely into Manuka's final renders. These couple of render engines I just talked about you cannot even touch, but the next one from DreamWorks Animation, called MoonRay, is actually free to use. MoonRay grew from a very ambitious idea, which is, instead of continuing to evolve an old render engine, DreamWorks wanted to rethink production path tracing around modern multi-core CPUs and massive render farms. You see, development stretches back more than a decade, but DreamWorks presented the architecture publicly at SIGGRAPH in 2017. The team essentially started from scratch, with no legacy render code, building a Monte Carlo path tracer which philosophy was to keep all the lanes of all the cores of all the machines busy. This meant heavily vectorizing ray tracing, shading, texturing, and integration using technologies such as Intel's Ampere and ISPC, while DreamWorks' Arras framework could distribute interactive rendering across different machines, which I think is really necessary in big productions. The reason DreamWorks invested in this, rather than simply standardizing on something like RenderMan or simply Arnold, was largely control and scalability. You see, they wanted rendering technology designed specifically around their enormous animated productions. Because remember, this is a huge animation company where artists might interactively work with huge environments, crowds, hair, volumes, and thousands of lights. And DreamWorks themselves said the original goal was creating something fast, interactive, and highly scalable. In other words, MoonRay wasn't merely about making final frames prettier, so to speak. I would say it is about shortening the distance between when an artist changes something to when the artist sees something close to the final result. And the first real proving ground was the short Bilby in 2018, but MoonRay's big feature debut came with How to Train Your Dragon, the hidden world, back in 2019. And you can understand why they wanted a new render engine to be central to that movie, because some sequences contained more than 1500 dragons, while the main character's dragon scale armor contained more than 3600 scales, alongside enormous environments, fire, atmospheric effects, and the glowing hidden world itself. VFX supervisor Dave Walford went as far as saying the film would not have been possible without the render engine MoonRay. So as you can imagine, from there, it effectively became DreamWorks' standard render engine. From Abominable, Trolls World Tour, The Croods: A New Age, The Bad Guys, Puss in Boots, The Last Wish, Kung Fu Panda version 4, The Wild Robot, and The Bad Guys 2 are among the productions rendered with it. And DreamWorks themselves said that every internally produced feature since How to Train Your Dragon back in 2019 has actually used MoonRay. What's unusual compared to what as Manuka or Framestore's Freak is that DreamWorks eventually decided not to keep MoonRay locked, inside the studio. So it announced the render engine as open source in 2022, released publicly under Apache 2.0 back in 2023, and in 2026, MoonRay became an Academy Software Foundation hosted project. So something originally created to solve DreamWorks' own rendering problems has effectively become a production render engine that any studio, or even you as a 3D artist, you can use and build upon. On the other hand, Framestore has an in-house render engine called Freak, which has an interesting origin, because the studio actually came to it after years of relying on commercial render engines. You see, for Gravity in 2013, Framestore integrated Arnold into its pipeline, because the movie demanded sophisticated, multi-balance path tracing, but that experience also made the studio realize how valuable it would be to control the render engine itself. So development of what became Freak grew during the following years, under people including Nathan Wolster, alongside Framestore's new layer shading system, whose concept dates to around 2013. As you can imagine, other than constantly writing one-off shaders for skin, metal, fabric, buildings, and other materials, Framestore wanted artists to construct complex materials from reusable physical layers, and having its own render engine meant the rendering and shading architecture could evolve together, which is great. So Freak eventually became an Embry-based path tracer. And if you're wondering, this means it uses Intel's Embry ray tracing technology, underneath, but Framestore controls the renderer, sampling, shaders, volumetrics, and pipeline built around it. But why did they do that? Well, the reason for doing this, instead of simply staying with Arnold, wasn't that Arnold was not fulfilling their needs. Framestore simply wanted technical independence. To see, if a production needed a strange new shader, better volumetric sampling, support for gigantic numbers of lights, or some experimental rendering techniques, its engineers could implement it themselves instead of waiting for commercial vendors' roadmaps, which can take months and sometimes years. But how did they do that in practice? Well, Framestore's layered material technology received an important early workaround, specifically on Guardians of the Galaxy back in 2014, particularly the enormous Nowhere environment, which contains millions of structures requiring lots of different material treatments. So Freak itself matured over subsequent productions, for example with Alita the Battle Angel, which became a major milestone and one of the first productions where Framestore rendered substantial work with the new system. And it was subsequently used on projects such as Avengers Endgame and Spider-Man Far From Home. And since then, it has essentially become Framestore's main render engine. As you can imagine, this long-term plan paid off in a pretty literal way, because in 2026, Framestore received an Academy Scientific and Technical Award for Freak's integral layered shading system, recognizing the work of John Bainbridge and Nathan Wolster. and Framestore themselves said that this new tech has contributed to the vast majority of his films, ranging from Paddington and Prehistoric Planet to the movie F1. Pixar's RenderMan is a little bit different from Manuka, Freak, or MoonRay, because its origins go back almost to the birth of Pixar itself. The technology grew from computer graphics research done by people such as Ed Catmull, Lauren Carpenter, and Rob Cook at Lucasfilm's computer graphics group during the early 1980s. So after that group became Pixar in 1986, the rendering work evolved into the RenderMan interface specification and RenderMan renderer, formally introduced in 1988. Its famous original architecture was RACE, which stands for Renders Everything You Ever Saw. This was designed for an era when brute force ray tracing was simply far too expensive. And here's the thing, instead of doing that, RACE subdivided complex surfaces into tiny micro-polygons and used clever approximations for things like shadows, reflections, and lighting, allowing filmmakers to render images that looked really realistic, especially for the 90s and the 80s era. So Pixar needed this tech because there really wasn't an off-shell, or as we say, commercial render engine capable of what the company was trying to do. So Pixar was effectively inventing the production techniques at the same time it was inventing the movie. And this level of control meant RenderMan could evolve alongside Pixar's pipeline, rather than Pixar having to design its movies around somebody else's software. Interestingly enough, Pixar didn't keep it completely proprietary, because what they actually did was smart. RenderMan became a commercial product and an industry standard used by many other studios, particularly ILM, which helped make it one of the most influential render engines ever created. And the project list of RenderMan is almost ridiculous, because it helped create landmark VFX in The Abyss back in 1989 and Jurassic Park in 1993, before becoming the render engine behind Toy Story in 1995, the first fully CG animated feature, and it has remained Pixar's core rendering technology for more than 30 years. But today's RenderMan is radically different, I mean from the Toy Story version. You see, Pixar gradually added ray tracing and global illumination during movies such as Ratatouille in 2007 and Up in 2009, before making its biggest architectural break with RenderMan 19, which abandoned the old race approach in favor of Monte Carlo path tracing. And Finding Dory in 2016 became one of the major showcases for this new physically based workflow, followed by Coco, Incredibles 2, Toy Story 4, Soul, Elements, and Inside Out 2, while the render engine itself has simultaneously been used outside Pixar on everything, from Star Wars to Marvel movies and other productions. So unlike most proprietary studio render engines, Pixar basically did both things at once. I mean, it built a render engine specifically to solve its own filmmaking problems, then turned that render engine into a technology which the rest of studios could use. And by the way, all Disney animation studios also have their own in-house render engine, called Hyperion. Hyperion was born around 2011, when Disney's rendering team began experimenting with a much more physically based approach. And by the time Big Hero 6 entered production, Disney wanted to create San Francisco at a scale its existing rendering pipeline would actually struggle with. So the finished city had roughly 83,000 buildings, 200,060 trees, 100,000 vehicles, and more than 200,000 streetlights, while characters such as Baymax needed convincing translucent materials and some scenes needed huge amounts of indirect illumination. As you can imagine, Disney wanted something custom too, so rather than simply adopting a commercial render engine, they developed Hyperion as its own physically based path tracer, giving its artists complete control, over how it handles Disney animation projects. And one of the cleverest ideas is that instead of tracing millions of rays independently, in essentially what you can say random directions, Hyperion kinda sorts huge batches of rays by direction and processes similar rays together, improving memory coherence and making enormous scenes much more practical. Disney has actually said that this move toward brute force physically based rendering was partly about artist efficiency, but what does that mean? Well, they said instead of lighters building lots of cheats in addition to some approximations, they could increasingly create plausible lights and materials and let GI do the hard work. And Disney didn't just build a proprietary engine simply for the sake of owning one, as you can see. So in practice, Big Hero 6 became Hyperion's first for production and was a fairly serious gamble, simply because the render engine was still being developed while the movie itself was being made, and Disney itself reportedly kept Pixar's RenderMan as a fallback plan in case Hyperion wasn't production ready, but at the end it worked, and from there, Hyperion became the foundation of Disney animation rendering pipeline. And by the way, Zootopia pushed it even further, through different environments, ranging from icy to humid rainforests, and Moana as a movie pushed actually huge tropical environments, vegetation, skin, volumes, and especially water, which gave it a real cast. And Frozen Adventures provided another early production showcase. Now let's talk about Animal Logic's Glimpse, which has a particularly nice origin story because it wasn't originally supposed to become the studio's main render engine, not even close. So around 2011, Animal Logic lighting supervisor Max Liani began developing a physically based shading system called PHX, and in his own time, he started experimenting with a small interactive path tracer that became Glimpse. The name literally came from its purpose. It allowed lighting leads and TDs to have a glimpse of what the lighting might look like, before committing to the expensive final renders. Animal Logic officially dates its development as an interactive lighting render engine to 2012, on the film Walking with Dinosaurs. The first version was extremely basic, as you can imagine. It was just gray shaded models, area lights, and some ray tracing, but it gave artists fast feedback about real lighting. And during the LEGO movie back in 2014, it evolved into a strange hybrid named Franken Glimpse, where Pixar's RenderMan and Glimpse actually ran together, with RenderMan handling parts of the established pipeline while Glimpse supplied fast ray tracing operations. And by the end of that production, Glimpse had advanced enough to finally render a handful of shots. The studio then made the bigger decision to turn it into a complete and directional path tracer, and the logic behind building their own render engine was quite practical. A commercial render engine had support to thousands of workflows and customers, whereas Animal Logic could make Glimpse lean, fast, and specifically optimized for their own movies. And owning both render engines and shading technology could also mean their developers could redesign them together, while the studio pursued the render everything idea, essentially trying to put the same physically based render engine into artist interactive viewports and final renders, rather than maintaining completely different preview and final render systems. But the real shift I think happened with the movie The Lego Batman, back in 2017, which became the first studio's feature rendered entirely with Glimpse. And that was a serious stress test, because Gotham contained enormous brick-built environments, thousands of lights, complex volumetrics, and shots reaching trillions of primitives. So Animal Logic expanded Glimpse with programmable shading, displacement, subdivision surfaces, curves for hair and fur, emissive volumetrics, and much better scene scalability. So Lego itself was also surprisingly demanding to render realistically, because translucent plastic required sophisticated subsurface scattering, while the miniature photography look pushed Animal Logic to calculate things such as depth of field and less distortion directly in the render engine, rather than relying entirely on compositing. From there, Glimpse became Animal Logic's primary render engine, and they used it in all their projects. And they were acquired by Netflix Animation Studios, as you probably know. And I kept one of the best for last, which is called DNGR, and there is an important distinction between Double Negative's DNGR and the other engines, because unlike the other engines, DNGR was never DNG's general purpose production render engine. The name stands for Double Negative Gravitational Renderer, and it was created specifically for Christopher Nolan's Interstellar, which was released in 2014, because normal commercial render engines weren't designed to answer the question which the director was asking: what could the camera actually see next to a rapidly spinning black hole? DNG's chief scientist Oliver James, in addition to a small development, worked closely with Caltech physicist Kip Thorne, who was the film's scientific advisor, turning the mathematics of Einstein's general relativity into production-ready rendering code. And DNG says the intensive development took about 7 months, while the whole project or the collaboration lasted over a year. And to make it, they did something really interesting. Instead of tracing light through ordinary Euclidean 3D space, like Arnold or RenderMan, The DNGR calculated how bundles of light rays travel through curved time-space around a rotating curved black hole, including extreme gravitational lensing. Using ray bundles rather than simply individual rays was particularly important because the movie needed enormous IMAX resolution images without the stars flickering from frame to frame, and the resulting program grew to roughly 40,000 lines of C++ and ran across DNG's Linux render farm, sometimes using hundreds of machines. And this is where DNGR differs dramatically from the other studio render engines which we have discussed. Its famous production history is basically only Interstellar. It was basically created to render Gargantua, the enormous spinning black hole, as well as the movie's wormhole and gravitational lensing effects, with some of the resulting imagery later integrated into DNG's formal VFX pipeline and mantra for particular shots. But the render engine became much more interesting than a one-movie tool because the collaboration went in the opposite direction too. I mean, the filmmakers weren't merely borrowing science, the VFX software became useful for science too. So after the production, DNGR was adapted for research into gravitational lensing, and the DNG team published technical and scientific papers describing what they had learned from it. So DNG's team even received a CVMP Collaboration Award back in 2023 for this particular work. So I wouldn't put this specific render engine in the list as DNG's equivalent to RenderMan, but it was a really incredible tool nonetheless. And there you have it, guys. If you like this video, please give it a thumbs up. Also check out the description down below to get the necessary links to all the render engines mentioned right here. Thank you guys very much for watching, and I will see you in the next one.